this cloud of points. Every tutorial on PCA tells you the two arrows that just appeared are the principal components. Almost none of them show you why those two arrows, and not any other two. So let's actually see it. The goal of PCA is simple. Find the directions your data varies along most, and throw away the rest. But to find those directions, you first have to decide what varying means. So we start there. Variance is the average squared distance from the mean. In one dimension, it's the spread of a number line. 2 points close together, variance is small. 2 points far apart, variance is big. Nothing fancy. In 2 dimensions, most tutorials just give you the variance in each axis direction separately. Variance of x, variance of y, but that's already misleading because points rarely spread along the axes you happen to pick. The data doesn't care about your coordinate system. If you collect the variances and covariances into a matrix, you get the covariance matrix. Don't memorize the formula, just hold on to what it means. This matrix describes the shape of your data cloud, not just how far it spreads, but in what direction. And shape isn't a metaphor. Every 2D covariance matrix defines an ellipse, one ellipse, exactly. It's wide in the directions your data scatters a lot, narrow where it doesn't, and tilted to match the way the points actually lean. Change the data, the ellipse changes. Same matrix, same ellipse. Now the key question, that ellipse has 2 axes. What are they? They're the directions where, if you projected your data onto a line pointing that way, the variance would be either the largest possible or the smallest possible. They are the natural coordinates of your data. And those axes, the directions where the ellipse's shape is extreme, are exactly the eigenvectors of the covariance matrix. That's not a coincidence. It's the entire point of PCA. Eigenvectors of the covariance matrix are the principal components. The eigenvalues tell you the variance along each. Let me show this on actual numbers. Here are 5 points. I compute the mean, subtract it off, then compute the covariance matrix. 2 numbers on the diagonal, 1 on the off diagonals. Watch what happens when I extract the eigenvectors of that 2 by 2 matrix. 2 directions come out. I draw them at the center of the cloud, and they snap to the long and short axes of the data without me telling them anything about the points. That's the whole trick. Now, when your PCA library returns the first principal component, what it's actually handing you is the longest axis of that ellipse. Project your data onto it, and you keep as much of the original spread as a single direction can possibly hold. Project onto the second, and you get what's left. The narrow direction, smaller variance. One thing worth noticing, the 2 axes are always perpendicular to each other. That's not a PCA rule. It's a consequence of the covariance matrix being symmetric. Symmetric matrices always have orthogonal eigenvectors, which means your principal components never overlap in what they describe. Each one captures variance the others missed. Here's the cleanest way to think about it. PCA isn't computing anything clever. It's finding the frame your data has been living in the whole time and telling you which axes actually matter. The variance captured by each component is its eigenvalue, nothing more. Sort them largest to smallest, keep the top few, drop the rest. The drop-off in the ranking is where you decide to stop. Let's run this on something real. MNIST digits live in 784-dimensional pixel space. Every pixel is a coordinate. Run PCA, keep the top 2 components, and you get this. 3's bunched together, 0's bunched together. The geometry that was invisible in 784 dimensions is now sitting on a page. And if I reconstruct the digits from just the top 5 components, I get blurry ghosts. Top 20, readable, but smooth. Top 50, basically the original. The eigenvalues told us exactly how much information each component carried, and the picture confirms it.